Welcome, curious minds and sleepy thinkers. You've found a soft place to land, a quiet corner where the questions are vast and the pace is slow enough not to jolt you from your pillow cocoon. Tonight, we're going to drift gently into the story of celestial wanderers, those ancient travelers that have graced our skies for eons, whispering tales of cosmic beginnings. We'll tiptoe into the heart of a remarkable journey, a mission that sought to touch the untouchable and unveil the secrets held within these icy visitors. Imagine, if you will, a time long, long ago when the night sky was not just a canvas for dreams, but a living tapestry of omens and wonders. Before the glow of city lights blurred the stars, our ancestors looked up and saw these ethereal visitors, comets, painting streaks of light across the velvet dark. They were seen as harbingers, sometimes of change, sometimes of dread, sometimes of great fortune. A comet was never just a star. It was a message, a whisper from the cosmos, carrying with it the weight of superstition and the promise of the unknown. For centuries, they remained veiled in mystery, their true nature hidden behind their luminous tails and fleeting appearances. The very word comet itself, derived from the Greek word komets, meaning long-haired star, speaks to the awe and wonder they inspired, seen as stars with flowing celestial tresses trailing across the heavens like cosmic spirits. These ancient perceptions weren't merely poetic. They were deeply integrated into the fabric of human understanding of the world. A comet's sudden appearance could alter the course of history, influencing decisions of kings and empires. Think of the Great Comet of 1680, which captivated even the brilliant Isaac Newton, inspiring him to consider the universal laws of gravitation. Before that, the Halley's Comet, appearing roughly every 76 years, left an indelible mark on cultures across the globe, from the Chinese annals, recording its every passage, to its famous depiction on the Bayeux Tapestry, signaling the Norman conquest of England in 1066. In those times, a comet was not merely a rock and ice ball. It was a cosmic pronouncement, a direct communication from the divine or the fates, shaping destinies and fueling imaginations. Its very presence was a dramatic interruption of the predictable celestial order, a reminder of forces larger and more mysterious than any earthly power. But as the human mind began to stretch its wings, reaching for understanding beyond myth, a new kind of curiosity began to bloom. The whispers of superstition slowly gave way to the gentle hum of scientific inquiry. We started to ask not just what they meant, but what they were. What were these celestial visitors truly made of? Were they solid, like the earth beneath our feet, or something far more fragile, like a cosmic snowflake drifting on the solar winds? Where did they come from, these icy messengers that appeared seemingly from nowhere, only to vanish again into the deep, dark ocean of space, perhaps to return decades or even centuries later? And how, in the vast, swirling chaos of the early solar system, had they come to be formed? Each question was like a tiny shimmering star inviting us deeper into the cosmic night, gently pulling us away from the realm of legend and into the embrace of systematic observation and reasoned thought. Perhaps most profoundly, we began to wonder what stories they held about our own origins. Could these ancient icy time capsules, preserved in the cold embrace of the outer solar system for billions of years, tell us something fundamental about the very beginnings of life here on our blue planet? Were they merely silent observers witnessing the birth and evolution of planets? Or were they active participants in the grand cosmic dance that led to our existence, perhaps delivering crucial ingredients to a nascent Earth? These were not simple questions demanding a quick answer. Instead, they were profound invitations to ponder our place in the universe, to trace the threads of our existence back to the very dust from which we were born, to the primordial soup of the early cosmos. The idea that these remote, beautiful wanderers might hold a key to life itself was a truly breathtaking thought, a quiet revolution in our understanding of the universe's interconnectedness. And so, in the quiet corridors of scientific thought, a bold idea began to take shape. An idea so audacious, so unprecedented, that it felt almost like a dream, a whispered possibility against the backdrop of conventional exploration. What if, instead of merely observing these distant wanderers through the blurred lens of Earth's atmosphere, or with distant flybys, we could reach out and truly touch one? What if we could peel back its icy layers, not with a gentle caress, but with a deliberate scientific embrace, a controlled collision designed not for destruction, but for unparalleled revelation? This was the seed from which the Deep Impact mission would grow, a journey, not just of spacecraft, but of human curiosity, pushing the boundaries of what was thought possible. It was a mission designed to gain a better understanding of comets by doing something truly remarkable, something no one had ever attempted before, launching a spacecraft specifically to crash into one, creating a window into its ancient heart. Imagine the quiet courage it took to conceive of such a plan. To send a delicate piece of human ingenuity, a sophisticated robotic emissary, across millions of miles of empty space, not to land softly and gather samples, but to purposefully collide. It was a testament to our insatiable desire to know, to understand the universe, not just from afar, but by reaching out and interacting with its most enigmatic inhabitants. This was not about wanton destruction, but about profound revelation, about creating a momentary dramatic opening to peer into the pristine, untouched interior of a celestial body that had existed largely unchanged since the formation of our solar system. The very name Deep Impact resonated with the profound nature of this quest, suggesting a journey into the hidden depths of a comet's being, and perhaps into the deeper truths of our cosmic home, truths preserved in ice and dust. This evening, we will gently explore this incredible mission, allowing its story to unfold like a quiet stream flowing through a peaceful landscape. We will trace its journey from the initial spark of an idea, perhaps over a cup of coffee in a quiet lab, to the dramatic, breathtaking moment of impact millions of miles away, yet watched by eager eyes across the globe. And then, most importantly, we will linger on what it taught us. What secrets did Tempel 1, the chosen comet, a short-period comet, named after its discoverer, Ernst Wilhelm Leberecht Tempel, reveal when touched by human curiosity and kinetic energy? What new chapters did it add to our understanding of cometary science, and by extension, the very tapestry of our solar system's birth? This is not a hurried race through scientific jargon or a dry recitation of facts, but a gentle walk through a garden of cosmic wonders, where each discovery is a petal unfurling, revealing new layers of beauty and mystery, inviting us to simply wonder at the elegance of the universe and the ingenuity of the human spirit. So let us settle in, allowing our thoughts to soften and our minds to open to the gentle current of this cosmic tale. We will not rush, but rather we will drift, carried by the quiet wonder of exploration, as we consider the profound journey of Deep Impact and the ancient wisdom whispered by the comets themselves. This is a story of curiosity, of courage in the face of the unknown, and of the enduring human spirit that reaches for the stars, not just to admire them as distant points of light, but to understand the very essence of their silent, luminous existence, and perhaps our own connection to their deep cosmic past. It is a narrative that encourages us to embrace the vastness, to find comfort in the unknown, and to appreciate the intricate dance of matter and energy that weaves the universe into being. The beauty of these celestial visitors lies not just in their fleeting brilliance, their shimmering tales, but in their profound connection to the earliest moments of our cosmic story. They are like frozen echoes of the solar system's infancy, preserving within their icy hearts the very dust and gases from which the sun and planets were born. Much like ancient amber preserves a prehistoric insect, to study a comet is in a sense to travel back in time to glimpse the raw ingredients of creation before they were baked and molded into the planets we know today. This is why the questions surrounding them, what they are, where they came from, how they were formed, are not merely academic curiosities. They are fundamental inquiries into our own cosmic heritage, into the very genesis of our planetary home and potentially the seeds of life itself. Each answer, however small, illuminates a piece of the grand mosaic of our universe, adding another brushstroke to the breathtaking portrait of cosmic evolution. Consider the sheer audacity of the idea to send a probe across millions of miles of empty space, navigating with unimaginable precision, not to land softly, but to intentionally collide. It's a bit like trying to understand the intricate workings of a delicate ancient clock by gently yet purposefully striking it with a precision tool. Knowing that the impact, while seemingly disruptive, is the only way to reveal its innermost mechanisms. In this cosmic analogy, the precision tool is the impactor spacecraft traveling at an immense velocity, and the clock is a cosmic relic untouched for billions of years. The precision required the understanding of orbital mechanics to intercept such a small, fast-moving target, the sheer faith in human ingenuity and robotic autonomy. It's a symphony of science and dreams playing out on an astronomical scale. And yet, it was precisely this bold counterintuitive approach that promised to unlock secrets that had remained hidden for billions of years. Secrets veiled by the comet's own protective layers, awaiting a moment of profound revelation. The journey of deep impact was not just a physical one through the cold vacuum of space, enduring the harsh realities of radiation and immense distances. It was also a journey of the human spirit, a collective endeavor born from a shared yearning to push the boundaries of knowledge, to challenge the limits of what we thought was possible. Every calculation, every design blueprint, every component fabricated, every test performed was a testament to this unwavering pursuit of understanding. It was a quiet dedication often unseen by the wider world that propelled this mission forward, a gentle but persistent force, driven by the simple, profound desire to comprehend the universe that cradles us. And in this understanding, we find not only answers that fill our textbooks, but also a deeper appreciation for the intricate dance of the cosmos and our own small, precious, yet profoundly curious place within it. So as the night deepens and the world outside grows quiet, let us allow our minds to float freely. Carried by the gentle current of this cosmic narrative, we will move through the story of deep impact, not as a hurried recounting of facts and figures, but as a meditative journey into the heart of scientific discovery, punctuated by moments of awe and wonder. Each step will be taken slowly, each concept illuminated with the soft glow of metaphor, inviting you to wonder, to imagine, and to find a quiet sense of awe in the vast, beautiful, and mysterious universe that surrounds us. This is a story for the curious soul, for the mind that finds peace in pondering the grandest questions, and for the heart that is open to the quiet magic of the cosmos. It's a reminder that even in the immense, silent expanse of space, our human drive to explore and understand shines brightly, pushing us ever onward towards new horizons of knowledge and wonder. Let us drift now a little further back in time to an era when the mysteries of the cosmos were less about impact craters and chemical compositions and more about the raw visceral experience of witnessing the heavens. For millennia before the advent of telescopes and spacecraft, comets were not just objects of scientific curiosity. They were living, breathing entities in the human imagination, imbued with power and meaning. They were celestial dancers, sometimes graceful, sometimes terrifying, etching their fleeting presence onto the scroll of human history. Imagine an ancient civilization, perhaps stargazing from a vast open desert or from the towering ziggurats of Mesopotamia. Suddenly, a new star appears, not a steady point of light, but a luminous smudge growing day by day, developing a shimmering tail that stretches across the night. What thoughts would stir in their hearts? Fear, perhaps, that a dragon had come to devour the sun, or awe that a divine messenger had descended to deliver a prophecy. These feelings, this deep, almost primal connection to the sky, shaped how humanity first encountered comets. They were not merely astronomical phenomena. They were harbingers, omens, portents of change, often significant and sometimes unsettling. Kings would tremble, battles would be fought, and destinies would be foretold, all under the silent, watchful gaze of these icy wanderers. The famous Bayeux Tapestry, a woven chronicle of the Norman conquest, even depicts Halley's comet, a vivid testament to its impact on the human psyche. It was seen as a sign of William the Conqueror's triumph, a cosmic seal of approval for his audacious invasion. Such was the pervasive influence of these celestial visitors that their appearances were meticulously recorded, not just by astronomers, but by chroniclers and historians, forever weaving their light trails into the human narrative. They were seen as celestial spectacles, yes, but also as active participants in earthly affairs, influencing tides of emotion and the currents of human destiny. For centuries, this blend of awe, superstition, and burgeoning observation defined our relationship with comets. Philosophers like Aristotle pondered their nature, often concluding they were atmospheric phenomena, not truly celestial. This idea that comets were mere exhalations of the Earth persisted for a remarkably long time, a testament to how challenging it was to grasp their true cosmic journey without the tools we now possess. Their unpredictable arrivals, their dramatic displays, and their eventual fade into obscurity only deepened their mystique, reinforcing the notion that they were temporary earthly events, rather than vast, distant travelers. Yet even within this realm of folklore and limited understanding, the seeds of scientific inquiry were quietly beginning to sprout. Early astronomers, armed with nothing more than their keen eyesight and perhaps basic instruments like quadrants and astrolabes, began to meticulously plot their paths, noting their positions against the backdrop of the fixed stars. This was the quiet, painstaking work of laying the foundations for future breakthroughs, gathering data, however incomplete, that would eventually chip away at the layers of myth. It was like collecting scattered pieces of a vast ancient mosaic without yet knowing what the full picture would reveal. Then came a pivotal shift. The scientific revolution, a blossoming of rational thought and empirical observation, began to gently peel back the veil of ancient beliefs. Figures like Tycho Brahe in the late 16th century, with his remarkably precise astronomical observations, demonstrated that the comet of 1577 was definitively beyond the moon's orbit, thus proving it was a celestial body, not an atmospheric phenomenon. This was a crucial first step, a quiet but firm declaration that comets belonged to the grand orderly clockwork of the heavens, not the fleeting whims of earthly air. But it was Edmund Halley in the late 17th and early 18th centuries who truly transformed our understanding. Building on Newton's laws of gravity, Halley painstakingly calculated the orbits of several comets recorded in history, noticing a striking similarity in the paths of comets observed in 1531, 1607, and 1682. With an act of intellectual courage that still inspires awe, he posited that these were not separate comets, but the same comet returning periodically. He then famously predicted its return in 1758. When it did indeed reappear exactly as he predicted, it was a triumph of scientific prediction and a definitive blow to the ancient superstitions. Comets were no longer capricious spirits. They were predictable members of our solar system, albeit with vast elongated orbits. They became celestial timekeepers, their returns a testament to the elegant mathematical precision of the universe. This newfound understanding, however, merely opened the door to a new set of profound questions. We now knew they were celestial, and some were periodic, but what were they like up close? What were they made of? And what secrets did they hold about the origins of our solar system, secrets that were tantalizingly out of reach, hidden by immense distances and their own hazy envelopes? The Earth-based observations, even with increasingly powerful telescopes, were like trying to understand the intricate details of a distant flower through a thick, shimmering fog. The outlines were there, the general shape, but the delicate textures, the vibrant colors, the minute details, these remained obscured, and so the quiet whispers of curiosity grew louder, evolving into a collective scientific yearning to reach out to touch these ancient travelers. The space age dawned a new chapter in human exploration, where our reach finally extended beyond the confines of our atmosphere. It began with humble rockets, then sophisticated probes designed to brave the harsh vacuum of space and journey to distant worlds. It was only a matter of time before these pioneering spacecraft set their sights on the comets, these enigmatic remnants of creation. The first tentative steps into this new frontier of cometary exploration were taken in the 1980s. It was an era filled with a sense of boundless possibility, a time when humanity was just beginning to truly stretch its technological wings beyond the moon. These early missions were bold, daring voyages into the unknown, navigating vast distances with technology that by today's standards might seem rudimentary, but was cutting edge for its time. They were like the first hesitant dives into a deep, dark ocean, hoping to catch a glimpse of its hidden inhabitants. In 1985, the International Cometary Explorer ICE, a spacecraft originally designed for other purposes, was repurposed for a groundbreaking encounter with Comet Jacobini-Zinner. It was a pioneering flyby, the first time a spacecraft had directly passed through a comet's tail. Imagine the thrill, the anticipation, as this robotic emissary plunged into the ethereal cloud, sending back data from a realm previously only imagined. It was a brief, fleeting encounter, like a ghost passing through a mist, but it offered invaluable first glimpses into the plasma and dust environment surrounding a comet, confirming theories about the solar wind's interaction with the comet's coma. It was a triumph of adaptive engineering and scientific foresight, proving that direct interaction was indeed possible. But the true spectacle of this era came in 1986 with the return of Halley's Comet. This was a once-in-a-lifetime opportunity, a cosmic rendezvous that captured the world's imagination. No fewer than 5 different spacecraft from various nations embarked on a daring fleet of missions, collectively known as the Halley Armada. Picture them, these intrepid robotic explorers, racing across the solar system, converging on this one famous comet. There was the European Space Agency's Giotto, which performed a remarkably close flyby, risking damage from dust particles to snap unprecedented images of Halley's nucleus. The Soviet Union contributed Vega 1 and Vega 2, which not only encountered Halley, but also dropped landers onto Venus along their journey, a testament to the ambition of the time. Japan sent Sakigake and Suisei, adding to the global effort to unravel Halley's secrets. These flybys were extraordinary achievements. Giotto, in particular, provided the first close-up images of a comet's nucleus, revealing it to be a dark, irregularly shaped object, far from the bright, fluffy snowball many had envisioned. It was more like a cosmic potato shrouded in a veil of gas and dust. We received fascinating photos showing jets of gas and dust erupting from its surface, and even some dust samples were gathered from as close as 200 kilometers. These early images were like peering through a dusty window into a distant ancient room, catching tantalizing glimpses of its contents. We began to understand the nucleus was the true heart of the comet, the source of its spectacular tail. Yet despite these fascinating close encounters and the invaluable data they provided, the comets still held many of their fundamental mysteries close. We had seen their outer layers, observed their spectacular comas and tails, and even tasted their dusty plumes. But the deeper questions remained like locked chambers within a grand ancient library. What was their internal structure truly like? Was the nucleus a solid rock-hard core, or a loosely bound collection of ice and dust, like a fragile cosmic meringue? What were they made from precisely in their pristine, untouched interiors, beyond the sublimated gases and dust we observed? And perhaps most profoundly, how had they formed in the first place billions of years ago at the dawn of our solar system? These were the elusive questions that haunted the minds of cometary scientists, urging them to dream of new, bolder ways to unlock these ancient secrets. The limited nature of flyby missions, no matter how close, meant we were essentially still observing from a distance, albeit a much closer distance than before. It was like trying to understand the full complexity of a deep-sea creature by only seeing its shadow pass briefly in the murky depths. The surface revealed much, But the true essence, the deepest secrets, lay hidden beneath. The heart of the comet? Its nucleus remained largely an enigma, its inner workings a subject of theoretical speculation rather than direct observation. This accumulating body of unanswered questions, this persistent whisper of the unknown, created a fertile ground for truly innovative thinking. Scientists yearned for a more direct, more invasive method of inquiry. They desired to go beyond mere observation to literally reach into the comet and bring its ancient secrets to light. This unfulfilled scientific longing, this profound curiosity about the primordial building blocks of our solar system would eventually lead to the radical proposition of the Deep Impact mission. It was a realization that, to truly know the comet, to understand its deepest nature, a new kind of interaction was needed, one that would momentarily dramatically peel back the layers of cosmic time and reveal the core of these icy wanderers. The stage was set for a scientific endeavor unlike any before it, driven by the lingering mysteries that even the most ambitious flybys couldn't solve. The problem, as scientists saw it, was akin to trying to understand a wrapped gift without ever touching the contents inside. You could feel its shape, estimate its size, perhaps even guess at its weight, but until you opened it, the true nature of the gift would remain a mystery. Comets were like these perfectly wrapped presents from the early solar system, their pristine interiors protected by outer layers that had been altered by billions of years of exposure to the sun and cosmic radiation. To truly understand their primordial composition, to glean insights into the raw materials that gave rise to planets and perhaps life itself, one needed to look beneath the surface. So while missions like Giotto had provided stunning close-ups, they were still, in essence, superficial glances. They showed us the immediate effects of solar radiation on the comet's outer crust, the dramatic outgassing that created its luminous coma and tail. But what about the interior? The undisturbed core that had been frozen in time for 4.5 billion years? Was it a compact block of ice and rock like a frozen cannonball? Or was it a loose, fluffy aggregate of dust and ice, like a cosmic meringue full of empty space? The answer to this question had profound implications for our understanding of how comets formed and what conditions were like in the earliest days of the solar system. Consider the immense technical challenges of even getting close to a comet. They are small, relatively dim objects, often traveling at incredible speeds. Navigating a spacecraft millions of miles through the vacuum of space to intercept such a target requires almost unimaginable precision. A celestial game of billiards played on a cosmic scale. And once there, to simply observe their surface shrouded as it often is by gas and dust was one thing. To peer inside was another matter, entirely pushing the boundaries of what observational astronomy could achieve. The scientific community, driven by this profound yearning for deeper insight, began to consider more audacious approaches. They understood that the dynamic processes occurring on a comet's surface, the sublimation of ice, the ejection of dust, were constantly altering its outer layers. To truly sample the pristine material, one had to go deeper beyond the weathered crust. This intellectual challenge, coupled with advancements in spacecraft technology, began to foster a daring idea. If we couldn't just look inside, perhaps we could make a way to look inside. This thought, once perhaps dismissed as science fiction, slowly gained traction, moving from whispered ideas in conference halls to serious proposals in scientific papers. This was the intellectual climate, the quiet yet powerful undercurrent of unresolved questions that set the stage for the Deep Impact mission. It wasn't just a random act of scientific curiosity. It was a direct response to the persistent, profound unknowns that even a decade of pioneering flyby missions had failed to resolve. The scientific community had reached a point where passive observation, while valuable, was no longer enough. To unlock the deepest secrets of these ancient time capsules, a more proactive, more transformative approach was needed. The comets were calling, and humanity, through its ingenious spacecraft, was about to answer in a spectacularly unprecedented way. The goal was not to destroy a comet, but to gently, yet decisively reveal its inner workings. It was an act of surgical precision on a cosmic scale, designed to expose a fleeting glimpse of the primordial material hidden within. Imagine a doctor needing to understand a mysterious ailment deep within a body. Sometimes a simple scan isn't enough. A small, carefully planned incision is required to get a direct look, to gather a sample to truly understand. The Deep Impact mission was conceptually similar, a controlled incision into a comet designed to expose its pristine interior for a brief, invaluable moment of scientific scrutiny. This conceptual leap from passive observation to active interaction marked a significant evolution in our approach to understanding the cosmos. It was a testament to the ingenuity and courage of scientists who dared to dream beyond the conventional, pushing the boundaries of how we interact with the universe itself. Now, having glimpsed the quiet beginnings of our fascination with comets, and having felt the insistent tug of questions that even the most ambitious early missions couldn't answer, let us gently lean into the core of those enduring mysteries. Imagine the comet's nucleus not as a simple solid object, but as a sealed chamber, a cosmic vault holding secrets locked away for eons. What exactly lay within this icy heart? This question, more than any other, beckoned scientists forward, whispering promises of profound revelations. The challenges were immense. We could see the glorious coma, the ethereal tale, the cosmic artistry painted across the canvas of space. But these were merely the comet's outer garments, shed and reformed as it drew near the sun. Beneath these magnificent displays lay the nucleus often described as the dirty snowball. Yet even that seemingly simple description belied a host of profound unknowns. Was it a tightly packed sphere like a frozen cannonball, dense and unyielding? Or was it something far more delicate, a loosely bound collection of tiny fragments, like a cosmic dust bunny held together by the gentle whisper of gravity? This fundamental question of internal structure was paramount, for it held the key to understanding the very processes of planetary formation. If a comet's interior was porous and loosely aggregated, it would tell a different story about the chaotic collisions and gentle accretions of the early solar system than if it were dense and solid. Think of it like trying to understand a complex ancient building from the outside. You can admire its architecture, its weathered stones, its grand facade. But to truly comprehend its construction, its history, its purpose, you need to step inside to see the supporting beams, the internal chambers, the very materials used in its core. Comets were, in this sense, magnificent cosmic buildings whose interiors remained stubbornly hidden. The dust and gas that constantly streamed from their surfaces, forming the brilliant coma, acted like a perpetual mist shrouding the nucleus and making direct observation of its true surface, let alone its interior, incredibly difficult. It was a challenge of cosmic obfuscation, where the very beauty of the object was also its veil. Scientists longed to know the precise composition of this primordial material. Was it mostly water ice, or were other exotic ices present, such as carbon dioxide, carbon monoxide, or even more complex organic compounds? And what about the dust? Was it fine like powdered sugar, or coarse like granular sand? The type of dust, its size, and its distribution within the icy matrix could reveal much about the conditions in the protoplanetary disk from which the solar system condensed. Imagine that disk as a colossal swirling pancake of gas and dust, cooling and clumping over millions of years. The comets were thought to be frozen relics of the outer colder regions of this pancake, preserving the original recipe of the solar system before it was cooked and transformed into planets. These questions were not merely academic curiosities. They held profound implications for understanding the grand narrative of our cosmic origins. If comets were indeed pristine remnants, largely unaltered since their formation, then studying their internal composition was akin to opening a time capsule from the dawn of our solar system. The materials found deep within their cores could provide direct evidence of the very ingredients that were present when the sun and planets were first coalescing from the stellar nursery. It was a quest to understand the primordial soup, the fundamental building blocks from which everything we see around us, including ourselves, ultimately emerged. Furthermore, the very formation process of comets remained largely speculative. Did they grow slowly, bit by bit, through gentle collisions of dust grains and ice crystals, like a snowflake, gradually accumulating more and more frosty adornments? Or were they formed in more violent chaotic events, perhaps from the collapse of larger icy bodies? The internal structure, whether it was tightly packed or loosely aggregated, would provide crucial clues to these early formation scenarios. If they were loosely bound, it might suggest a gentler, more gradual accretion process, where particles slowly stuck together without much compaction. If they were dense, it could point to more energetic collisions or gravitational collapse. Each possibility painted a different picture of the primordial dance that gave birth to the cosmos we inhabit. Consider the immense distances involved and the transient nature of comets when they become observable. For most of their long, lonely lives, comets reside in the far frigid reaches of our solar system in vast spherical reservoirs like the Oort cloud or the Kuiper belt. They are like cosmic sleepers, drifting silently in the deep freeze of interstellar space, far beyond the reach of our telescopes. Only occasionally stirred by a gravitational nudge from a passing star or planet do they begin their long, slow plunge inward towards the sun. As they approach, the sun's warmth begins to awaken them, causing their frozen gases to sublimate and creating the beautiful, albeit obscuring, coma and tail. This fleeting period of activity, though visually stunning, also makes them challenging to study directly, as their true surfaces are hidden by the very processes that make them visible. It's like trying to photograph a delicate ice sculpture through the steam it emits as it melts in the sun. The prevailing theories about cometary formation and composition were largely based on indirect observations, laboratory experiments simulating icy conditions and theoretical models. While these provided valuable frameworks, they couldn't replace the direct evidence that a physical interaction with a comet's pristine interior could provide. Scientists felt a profound need to move beyond speculation to obtain ground truth from one of these ancient objects. It was a quest for empirical certainty, a desire to anchor our theories in the tangible reality of a comet's heart. This yearning for direct access fueled a growing frustration with the limitations of simple flyby missions. While missions like those of the Halley Armada in 1986 provided tantalizing glimpses, they were like fast cars zooming past a fascinating landscape. You could snap a few pictures, note some prominent features, but you couldn't stop, get out, and truly explore. The spacecraft would gather data for a few precious minutes or hours, then rush onward, leaving behind a trail of unanswered questions. The resolution of the images, while groundbreaking for their time, was still not enough to discern fine details about the nucleus's composition or internal layering. The dust and gas, while part of the comet's allure, were also frustrating veils obscuring the very core that scientists yearned to study. Imagine a detective trying to solve a very old mystery where the only clues are faded photographs and distant echoes. The detective knows the critical evidence is hidden, perhaps buried deep within a long-lost vault. The challenge is not just finding the vault, but opening it to reveal its contents. For cometary scientists, the vault was the comet's nucleus, and the evidence was its primordial, unaltered material. The existing tools were insufficient for the task. They needed a new approach, a cosmic pickaxe, to gently but effectively pry open that vault. And so the quiet discussions began leading to a truly revolutionary idea. What if we didn't just fly past a comet, but actually into one? Not in a destructive, uncontrolled way, but with a deliberate, precisely engineered impact. The notion was audacious, bordering on the seemingly impossible, yet it held the promise of unlocking a treasure trove of information that no other method could provide. It was a paradigm shift in cometary exploration, moving from passive observation to active probing investigation. This wasn't just about collecting data. It was about creating the data, forcing the comet to reveal its secrets. The core problem, as articulated by the scientists, was how to understand the internal structure of comets by simply looking at their surface. It was clear that the surface was weathered, altered by billions of years of solar radiation, cosmic rays, and the vacuum of space. It was like trying to understand the fresh, soft interior of a cake by only looking at its hardened, crusty exterior. To know what was truly going on, scientists would need to dig a little deeper to penetrate those outer layers and expose the pristine material beneath. This was the fundamental scientific imperative that drove the concept of an impact mission. It was a direct response to the limitations of previous missions and the persistent mysteries that haunted the field. This yearning to dig deeper also stemmed from a desire to resolve conflicting theories. Some models suggested comets were relatively homogeneous bodies like solidified icebergs, while others proposed a more layered, fragile structure, almost like a collection of building blocks loosely stacked together. Only a direct interaction, a physical penetration, could definitively distinguish between these possibilities. An impact would create a fresh crater, exposing a cross-section of the comet's interior, allowing instruments to analyze the ejected material and the new surface uncorrupted by billions of years of solar exposure. It was the scientific equivalent of taking a biopsy, a small, carefully planned intrusion to gain crucial diagnostic information. Moreover, the behavior of dust and ice within a comet was a significant area of uncertainty. How were these materials bound together? What was their density inside the nucleus, not just at the surface? The answers to these questions would inform our understanding of the forces at play during comet formation and evolution. Imagine trying to understand how a snowdrift forms and behaves. You can look at its surface, but until you dig into it, you don't know if it's fluffy and easy to push through or compacted and surprisingly solid. An impact would provide this kind of digging, offering a direct probe into the mechanical properties of the comet's interior. The inherent challenges of such a mission were themselves a testament to the depth of the mysteries. Could a spacecraft even hit such a small, distant, fast-moving target with the required precision? What would happen upon impact? Would the material be so loose that the impactor would just punch through like hitting a snowdrift, creating no discernible crater at all? Or would it hit a surprisingly hard, frozen shell like striking solid rock? These were not just engineering questions. They were fundamental scientific uncertainties about the nature of comets themselves. The very act of planning the mission forced scientists to confront the limits of their current knowledge, to acknowledge the vastness of the unknown. And this is where the profound beauty of scientific exploration truly shines. It's in the humility of admitting what we don't know and the courage to devise new, ingenious ways to find out. The idea of deep impact wasn't born out of arrogance, but out of a deep-seated intellectual curiosity and a recognition that the universe held secrets that would not yield to traditional methods. It was a call to innovation, a challenge to human ingenuity to transcend the limitations of distance and direct observation. So the stage was set. The questions were clear. What was inside the comet? How was it put together? And what could these answers tell us about the very dawn of our solar system? These profound inquiries, simmering for decades, would eventually coalesce into a single bold plan, a mission that promised to rewrite our understanding of these ancient wanderers. It was a testament to the fact that sometimes to find the deepest truths, one must dare to make a deep impact. The scientific community yearned to peel back the veil, not just of gas and dust, but of cosmic time itself, to glimpse the pristine core of a celestial relic. This desire to touch the untouched, to reveal the hidden, was the driving force, the quiet engine behind the remarkable journey that was about to unfold. With the lingering questions about comets echoing in the minds of scientists, the stage was set for a truly audacious proposal. If direct observation couldn't fully reveal a comet's internal secrets, then a new, more forceful method was needed. And so, in 1999, a plan began to crystallize within NASA, a blueprint for a mission that would push the boundaries of space exploration. It was a proposal to hope to answer some of these deep fundamental questions, not by gently observing, but by creating a dramatic, yet precisely controlled interaction. The core idea was elegantly simple, yet profoundly challenging. To understand the hidden layers of a comet, scientists would need to dig a little deeper. Their plan was to create a crater in a comet, a fresh wound in its ancient surface, using a precisely aimed spacecraft called an impactor. This impactor, not unlike a high-speed intelligent bullet, would collide with the comet at immense velocities designed to excavate a hole revealing the pristine material beneath. Imagine a geologist wanting to understand the composition of an ancient mountain. Looking at its weathered surface might tell you something, but drilling a core sample or creating a controlled blast to expose a fresh cross-section would yield far more precise and invaluable information. The Deep Impact mission sought to do just that, but on a cosmic scale with a celestial body traveling millions of miles away. The beauty of this seemingly blunt approach lay in its scientific precision. Scientists would know the exact mass of the impactor and the precise speed it was traveling at just before collision. These known quantities were crucial. From the size of the impact crater that would be created, and by carefully observing the material ejected from it, they could calculate valuable information about the comet's properties. For instance, if the impact created a very large crater for the given energy, it would suggest the comet's surface was a loose aggregate of dust and ice, easily displaced, much like hitting a pile of fluffy snow. Conversely, if the crater was small and shallow, it would indicate a much tougher, harder frozen shell, perhaps like striking a block of solid ice or rock. This kinetic test was the ingenious way to infer the internal strength and porosity of a body billions of years old without ever having to physically touch it with human hands. This method was a direct answer to the lingering questions about internal structure. Previous flybys could only hint at the comet's density through gravitational measurements or by observing surface features. But an impact creating a visible measurable cavity would offer direct empirical evidence. It was like finally being able to test the consistency of that cosmic potato or cosmic dust bunny we spoke of earlier, pushing a finger into it to feel its true texture. The ejected material itself, flung out into the vacuum of space, would also be a treasure trove of information. Light from the sun reflecting off these newly exposed particles, or even the faint glow from sublimating gases, could be analyzed by sophisticated instruments on a companion spacecraft, revealing the chemical composition of the comet's pristine interior. This was a profound shift in methodology from passive observation to active probing experimentation, allowing the comet to literally reveal its inner secrets in a dramatic cosmic spectacle. The choice of target was critical. It needed to be a comet that was scientifically interesting, accessible, and safe to approach. After careful consideration, the scientists set their sights on a short-period comet called Tempel 1. Short-period comets, those with orbital periods typically less than 200 years, are thought to originate from the Kuiper Belt, a region beyond Neptune. This makes them relatively fresher than long-period comets from the Oort cloud, as they haven't made as many passes near the Sun that could alter their composition. Tempel 1 was an ideal candidate. Its orbit was well understood, making navigation precise, and it was active enough to exhibit cometary behavior, yet not so active that its coma would entirely obscure the impact site. Its relatively frequent returns to the inner solar system also made it a more accessible target for a mission. Imagine this chosen comet, Tempel 1, as an ancient weathered ship, sailing a predictable, well-charted course through the cosmic ocean. Its nucleus, the heart of the ship, was known to be roughly 8 kilometers long and 5 kilometers wide, an irregularly shaped lump of ice and dust, like a colossal cosmic peanut or a giant dark potato tumbling through space. It was not a perfectly smooth sphere, but rather a rough pockmarked relic bearing the scars of billions of years of cosmic bombardment and solar weathering. This irregularly shaped nucleus, a frozen monument to the early solar system, was the precise bullseye for humanity's most ambitious cometary experiment. Yet despite all the careful planning and scientific rationale, scientists weren't exactly certain what would happen when the impactor hit. This wasn't a flaw in their planning. It was a testament to the very unknowns they sought to unravel. There was a genuine sense of anticipation and acknowledgement that the universe often holds surprises. Perhaps one theory posited the impactor would simply punch straight through like hitting a very loose snowdrift, creating no real crater at all, with the impactor disappearing into the fluffy interior. This would suggest an incredibly porous, fragile structure. Other theories predicted a more resilient surface, perhaps a hard frozen shell, where the impactor would create a more defined, yet still potentially small crater, akin to cracking a thick sheet of ice. There were many such theories, each painting a slightly different picture of Tempel 1's hidden nature. The scientific community was buzzing with these possibilities, eager to find out which was correct. Which hypothesis would be confirmed by the dramatic real-world experiment that was being planned? This embrace of uncertainty, this genuine curiosity about the unknown outcome, is a hallmark of true scientific inquiry. It's not about proving what you already believe, but about designing an experiment that allows the universe to reveal its own truth, no matter how surprising it might be. This level of detailed planning and scientific foresight ultimately convinced the powers that be. After thorough review and assessment of its ambitious goals and potential for groundbreaking discoveries, NASA approved the project, giving it a budget of $330 million. This significant investment was a clear signal of the mission's perceived scientific value and the agency's commitment to pushing the frontiers of space exploration. The mission was officially named Deep Impact, a name that perfectly encapsulated its core concept, a profound probe into the very depths of a celestial body designed to create a lasting mark on both the comet and our understanding of the cosmos. You might have thought that this name was a direct reference to the 1998 Hollywood film of the same name, which depicted a giant comet on a collision course with Earth and a desperate mission to intercept it with nuclear weapons. The timing was certainly uncanny. However, the official story from NASA was that the names for both the project and the film had been come up with independently around the same time. What a remarkable coincidence, if so a curious twist of fate where art and science converged on a shared vision of a cosmic impact. It's certainly a notion that sparks the imagination, a moment where the grand narratives of fiction brushed shoulders with the bold realities of scientific exploration. There certainly did seem to be some uncanny similarities between the film and the NASA mission, especially given that NASA scientists had reportedly even worked on the film as consultants. One might find it difficult to entirely buy NASA's claim of a mere coincidence, allowing a small playful skepticism to linger. Perhaps it was a subtle nod, a quiet acknowledgement of the cultural zeitgeist, or simply a reflection of how deeply the idea of cosmic impacts resonates within the human collective consciousness. The allure of such a dramatic event, whether fictional or real, speaks to our inherent fascination with cosmic forces and our place within their immense power. Fortunately for the Earth, however, there were some crucial differences between the film and the mission. For one, Tempel 1's orbit was nowhere near the Earth's. There was absolutely no risk of it impacting our home planet. This mission was purely about scientific discovery, not planetary defense. Furthermore, and perhaps most reassuringly, given the immense size of the impactor compared to the comet, there was no chance of knocking it off its current trajectory by more than a centimeter or so. This was a crucial point often misunderstood by the public and carefully emphasized by NASA. The mission was not about altering the comet's path, but about briefly gently opening a tiny window into its ancient self. To put the scale into perspective, it would be more like a fly hitting the front windscreen of a large vehicle. The vehicle in this case being Comet Tempel 1 would continue its journey largely undisturbed, merely experiencing a tiny, almost imperceptible tremor from the encounter. The fly, our intrepid impactor, would be utterly consumed by the interaction, but its brief, powerful existence would serve a grand scientific purpose. This metaphor vividly illustrates the minuscule scale of the impactor, relative to the comet, underscoring that the mission was about precise scientific probing, not cosmic demolition. Additionally, and again quite thankfully, nukes would not be necessary to create a crater on Tempel 1, or any kind of explosives for that matter. The power came not from chemical reactions, but from the raw, unadulterated force of motion. The sheer speed and kinetic force the impactor would possess when it collided with the comet's surface would be more than enough to create the desired crater. Imagine the energy unleashed when a small object traveling faster than almost anything we experience on Earth suddenly meets resistance. This was the principle behind deep impact. The impactor itself, traveling at approximately 37,000 kilometers per hour, about 23,000 miles per hour, relative to the comet, would deliver an immense amount of kinetic energy upon collision. It was predicted that this immense energy would create a crater roughly 100 meters across and 30 meters deep. A cosmic splash designed to reveal. This careful calculation of kinetic energy versus explosive force highlights the elegance of the mission's design. It wasn't about brute power, but about understanding the precise physics required to achieve the scientific objective. The impact would be a testament to the power of velocity, a demonstration of how even a relatively small mass, when accelerated to extreme speeds, can deliver a profound and revealing punch. The theoretical predictions for the crater size provided a crucial benchmark for the mission's success, a tangible goal for the scientific experiment being conducted millions of miles away. With the mission given the green light and its audacious concept firmly established, scientists began the intricate work of building the Deep Impact spacecraft. This was not a single monolithic entity, but a sophisticated multi-part instrument designed to execute a complex ballet in the cold vacuum of space. The spacecraft was actually made with two distinct parts: the payload, which was the actual impactor designed to hit the comet, and another larger mothership designed to carry it through space, release it at the opportune moment, and then observe and record the spectacular result of the impact from a safe distance. This second larger section was aptly named the flyby spacecraft. This dual design was crucial for the mission's success. The flyby spacecraft, which housed most of the sensitive scientific instruments and communication arrays needed to survive the impact event and continue to transmit the invaluable data back to Earth. It was the eye and ear of the mission, meticulously observing the dramatic interaction it had just orchestrated. The impactor, on the other hand, was a sacrificial lamb destined for a glorious, brief, and incredibly impactful existence. This separation of roles allowed for optimal performance from both components, maximizing the scientific return from this unique cosmic encounter. The intricate coordination required between these two independent but interdependent spacecraft was a marvel of engineering, a silent testament to human ingenuity reaching across the vast emptiness of space. With the bold concept of deep impact now firmly approved and its scientific objectives clear, the intricate work of bringing this vision to life began. This wasn't merely about designing a single probe. It was about orchestrating a complex ballet between two interconnected spacecraft, each with its own crucial role. The challenge lay not just in reaching a distant comet, but in precisely choreographing a dramatic collision and capturing every fleeting moment of its revealing aftermath. The first of the two parts was the flyby spacecraft, the larger of the two, acting as the mission's silent observer and chronicler. Imagine it as a cosmic photographer and data collector positioned to witness the main event from a safe yet privileged vantage point. It weighed 600 to 1 kilograms, roughly the size of a small car, and stretched about 3 meters long. This mothership was a sophisticated hub housing the bulk of the mission's sensitive scientific devices, the crucial communication systems, and its own power source. Its broad solar panels were like diligent wings, constantly turning towards the sun to drink in the energy needed to power its complex systems and send its precious findings across the vastness of space back to Earth. Recognizing the chaotic nature of a cometary environment, especially after an impact, the flyby spacecraft was also equipped with a robust debris shield. This shield was like a protective cloak designed to guard its delicate instruments from any unexpected particles flung out by the comet, or even from the debris created by the impact itself. While it kept its distance, a tiny wayward piece of dust traveling at cosmic velocities could still be lethal to unprotected electronics. This shield was a testament to the meticulous planning, anticipating even the smallest, yet potentially catastrophic threats in the silent ballet of space. But the true eyes of the flyby were its two powerful cameras, the high-resolution imager HRI and the medium-resolution imager MRI. These weren't just ordinary cameras. They were specialized instruments designed to capture the dynamic events unfolding on a comet's surface with incredible clarity and precision. The HRI, as its name suggests, was a sharper, more focused lens capable of discerning fine details crucial for observing the exact impact site and the subsequent changes on the comet's nucleus. The MRI provided a wider field of view, essential for navigation and for capturing the broader spectacle of the dust plume and the comet's overall activity. Think of them as a pair of binoculars and a wide-angle lens working in tandem to capture both the grand cosmic canvas and the intricate brushstrokes of the impact event. These cameras served a dual purpose. Crucially, they would take breathtaking photos of the comet after the impact, documenting the size and shape of the newly formed crater and observing the properties of the ejected material. But beyond their role as post-impact witnesses, they also played a vital part in the mission's journey, helping with navigation. They acted like the flyby's eyes, constantly scanning the distant comet, providing crucial data for course corrections and ensuring the spacecraft remained on its precise trajectory for the rendezvous and observation. Their visual data was not just for pretty pictures. It was the bedrock of the spacecraft's autonomous guidance system, helping it to gracefully steer through the cosmic void towards its ancient target. The other part of this cosmic duo was the impactor itself, the smaller boulder and ultimately sacrificial component of the mission. It was a remarkable piece of engineering considering its fate. Weighing only 372 kilograms, about half the mass of the flyby, it was compact and robust. Despite its modest size and singular destructive purpose, it was still a remarkably smart piece of technology. It wasn't just a dumb projectile. It was equipped with its own dedicated intelligence, designed to autonomously guide itself to its final dramatic meeting with the comet. The core of its intelligence lay in its single dedicated camera, the Impactor Targeting Sensor, ITS. This wasn't just any camera. It was the impactor's equivalent of an eagle eye locked onto its prey. Its sole purpose was to precisely navigate the final moments of the impactor's descent onto Tempel 1. As the impactor separated from the flyby spacecraft, the ITS would begin a relentless stream of photos of Tempel 1, capturing images right up until the very moment of impact. Imagine it like a diver taking photos of the ocean floor as they plummet towards it, capturing every detail until the final splash. These images were not stored on board for later retrieval. They were immediately streamed back to its parent, the flyby spacecraft, which would then diligently relay these invaluable final close-up images to Earth. This meant that even as the impactor met its end, it was still performing its scientific duty, sending back data from a perspective no other instrument could achieve. These final breathtaking images, captured milliseconds before oblivion, would offer unprecedented views of the comet's surface, revealing details that were simply impossible from the flyby's safer distance. Beyond the technological marvels, the Deep Impact mission also managed to capture the public's imagination, becoming more than just a scientific endeavor. It was a public event. NASA, with its characteristic flair for engagement, actively encouraged considerable public interest in the mission. In 2003, they launched a unique initiative that invited members of the public to submit their names to be recorded on a CD, which would then be placed directly on the impactor. This was a brilliant stroke, transforming a distant scientific experiment into a personal journey for hundreds of thousands of people. Imagine the thrill of knowing your name, however small, was literally traveling millions of miles through space, destined for a dramatic, fiery, yet scientifically profound encounter with a comet. It was a tangible connection to the cosmos, a chance to be part of something truly extraordinary. Roughly 625,000 names were collected in this way, a silent legion of human curiosity carried directly to Tempel 1's ancient surface. It was a powerful reminder that while science is often conducted by a dedicated few, its wonder belongs to all. This simple act transformed the cold, sterile mechanics of spaceflight into a shared human adventure, inviting everyone to feel a connection to this unprecedented cosmic voyage. On top of this personal connection, NASA made another symbolic yet highly effective choice. They timed the impact to take place on the 4th of July, American Independence Day. This choice, steeped in national symbolism, undoubtedly added an extra layer of public excitement and patriotic fervor to the mission. While there may have been a practical scientific reason, it was just one day before Tempel 1's perihelion. Its closest approach to the Sun and its increased proximity to the Sun might have produced clearer images due to heightened cometary activity. There's a gentle suspicion that the more likely reason for this specific date was a touch of cosmic showmanship. One suspects that American scientists with a twinkle in their eye rather liked the idea of a large cosmic firework, a spectacular celestial display to mark a national holiday. It was a perfect fusion of scientific aspiration and public engagement, transforming a complex astronomical event into a universally accessible, awe-inspiring celebration. The actual journey began on January 12, 2005, when Deep Impact launched into the vast unknown atop a powerful Delta II rocket from Cape Canaveral, Florida. The launch itself was a symphony of power and precision, a fiery ascent into the dawn sky carrying humanity's boldest comet probe. For the engineers and scientists who had poured years of their lives into this mission, it was a moment of profound relief and exhilarating anticipation. The spacecraft was finally on its way, a delicate vessel beginning its long voyage across the cosmic ocean. But space, as often reminds us, is a realm of unforgiving realities and unexpected challenges. Within a day of leaving the Earth's orbit, a problem, a quiet hiccup in the complex machinery hit. Deep Impact's onboard computers suddenly switched itself to safe mode, a built-in protective state that it would only enter if there was a fault detected, a self-preservation instinct kicking in. This immediately sent a ripple of anxiety through the control rooms. What could be wrong so early in the mission? The diagnostic readouts suggested something on board was apparently overheating, a critical and worrying sign in the cold vacuum of space, where components are designed to operate within very specific temperature ranges. This unexpected glitch, so early in the mission, gave scientists a bit of a scare, a moment of profound apprehension. All the years of planning, the hundreds of millions of dollars, the collective hopes, could it all be jeopardized so quickly by an unforeseen technical issue? The tension in the mission control room must have been palpable, a quiet storm of concern as engineers scrambled to diagnose the problem. Every line of code, every sensor reading was scrutinized with intense focus, hoping to pinpoint the source of the anomaly before it could escalate. Fortunately, and with a collective sigh of relief that could almost be heard across the millions of miles, the cause of the problem was quickly found to be a minor programming issue. It wasn't a hardware failure, not a physical breakdown of a critical component, but a subtle error in the instructions given to the spacecraft's temperature sensors. The acceptable heat tolerances had been set too low in the software. This meant that Deep Impact's computers thought its thrusters were overheating, sensing temperatures that were technically above the programmed limit, when in reality they were just fine, operating well within their safe actual limits. It was a case of the alarm bell ringing unnecessarily loudly, triggered by an overly cautious internal setting. Once the engineers identified this subtle yet critical flaw, they immediately corrected the issue by uploading new software parameters. With the digital correction, Deep Impact was able to properly begin its mission, shaking off its early jitters and settling into the long silent journey ahead. This early scare, while stressful, served as a poignant reminder of the fragility and complexity of these robotic explorers and the constant vigilance required to guide them through the unforgiving environment of space. It was a test of the team's ability to diagnose and adapt a minor tremor before the much larger planned impact to come. The initial fear gave way to a renewed sense of purpose as the spacecraft, now fully operational, pointed itself towards Tempel 1, ready to embark on its cosmic quest. With the early hiccup gracefully resolved, Deep Impact, now fully awakened and on course, began the true expanse of its journey. The spacecraft settled into a rhythm, silently traversing the unfathomable distances of our solar system. It spent the next 6 months traveling to its rendezvous point with Tempel 1, a long, quiet voyage across the cosmic ocean. Imagine that half a year floating through the silent cold vacuum, a speck of human ingenuity hurtling towards an ancient distant target. During this immense journey, it covered an astonishing 429 million kilometers. To put that into perspective, consider the scale of our solar system. That's more than twice the distance from the Earth to the Sun, a truly staggering cosmic commute. This wasn't a sprint. It was a marathon of precision navigation and unwavering persistence. For the scientists and engineers back on Earth, these months were a period of vigilant monitoring, of checking telemetry, and of quiet anticipation. They knew the spacecraft was performing its intricate dance, but the silence of space meant their connection was limited to faint radio signals, like whispers carried on a cosmic breeze. Despite the vastness of the distance and the intricate dance of orbital mechanics, Deep Impact proved to be an exceptionally precise traveler. It had to course correct twice on the journey, subtle nudges and adjustments, to ensure it stayed precisely on track to meet its ancient quarry. This in itself was an impressive feat. In fact, it was originally planned for there to be 3 course corrections, but the initial trajectory and the first 2 adjustments were so remarkably precise that the third planned correction was deemed unnecessary. Imagine aiming a dart at a tiny moving target hundreds of miles away and hitting it so accurately that you don't even need your final adjustment. Such was the level of navigational mastery achieved by the team and the spacecraft's autonomous systems. This journey wasn't just about reaching a destination. It was about orchestrating a celestial ballet where both the spacecraft and the comet were moving at incredible speeds, yet their paths had to converge at a single precise point in time and space. The spacecraft's trajectory was calculated with exquisite detail, taking into account the gravitational tugs of the sun and planets, the faint pressure of solar radiation, and the tiny imperfections of its own propulsion system. Every millimeter, every second, mattered over these vast distances. It was a testament to the meticulous work of the navigation teams, who were essentially cosmic choreographers, ensuring their robotic dancer met its partner with unerring accuracy. As the 6 months drew to a close, a new sense of excitement began to ripple through the mission team. On April 25, 2005, Deep Impact caught its first glimpse of Comet Tempel 1. It wasn't a crisp, detailed image yet, but a faint, fuzzy smudge against the backdrop of distant stars. Think of it like spotting a distant ship on the horizon, just a hint of its form. For the scientists who had dreamt of this moment for years, this was profound. It was the confirmation that their tireless efforts were paying off, that their tiny emissary was indeed closing in on its ancient target. This initial sighting was the first visual confirmation of their success, a quiet cheer echoing across the vast distance. From this point on, the journey became even more critical and far more autonomous. Of course, NASA scientists couldn't manually guide Deep Impact in real time like steering a car. The sheer distances involved made that impossible. By this point, Deep Impact and Tempel 1 were roughly 130 million kilometers away from Earth. To put that in perspective, That's more than twice the closest distance between Earth and Mars. Imagine shouting a command and waiting more than 7 minutes for the sound to travel there, and then another 7 minutes for the reply. This immense signal lag meant that any real-time control was utterly impractical. Instead, Deep Impact had to rely on its own internal brilliance. Its smart onboard programming would have to guide it in for the final, most critical leg of the journey. This meant the spacecraft was imbued with an astonishing degree of autonomy, a capacity to analyze its environment, make crucial decisions, and execute complex maneuvers without constant human intervention. It was like sending a highly trained explorer into a distant, uncharted land, trusting them to navigate the final treacherous steps on their own. The algorithms, the pre-programmed sequences, the sophisticated image recognition software, these were the digital brains that would steer the impactor to its final rendezvous. The spacecraft's cameras, particularly the impactor targeting sensor ITS on the impactor itself, became its ultimate guide. These cameras would capture images of Tempel 1, and the onboard computer would analyze the position of the comet against the star field, making tiny, precise adjustments to its trajectory. This was a continuous feedback loop, a cosmic dance of vision and adjustment, ensuring that the impactor would precisely meet its target. It was a ballet of numbers and light executed with incredible precision, millions of miles from any human hand. As the days turned into weeks, the images from Deep Impact grew sharper, revealing more and more details of Tempel 1's rugged ancient surface. Each new picture was like a page turning in a cosmic history book, slowly unveiling the secrets of this primordial wanderer. Scientists watched with bated breath, studying every new feature, every subtle change in its outgassing, trying to anticipate what might lie beneath its weathered crust. The closer it got, the more real the mission became, transforming from a distant concept into an imminent reality. Finally, the moment arrived for the dramatic separation. On June 29th, just days before the scheduled impact, the impactor was successfully released from the flyby spacecraft. This was a critical and delicate maneuver. The flyby, acting as a wise parent, gently nudged its smaller child onto its final independent trajectory. The impactor, now on its own, continued its solitary plunge towards Tempel 1, its onboard targeting sensor locking onto its prey. The flyby, meanwhile, executed a subtle maneuver to reposition itself to a safe distance, an angle ready to act as the mission's primary observer. Its wide eyes fixed on the impending cosmic drama, the impactor then positioned itself into the comet's flight path to crash into it head-on. This specific approach was chosen for a few crucial reasons, each carefully calculated to maximize the scientific return. First, and perhaps most intuitively, a head-on collision meant that the front of the comet was in sunlight. This was critically important for visibility. Imagine trying to film a dramatic event in complete darkness. It would reveal nothing. The sunlight ensured that the impact site, the ejecta plume, and the newly formed crater would be illuminated, providing optimal conditions for the flyby's cameras to capture clear, detailed images. The sun's light was not just a source of warmth. It was the essential spotlight for this cosmic performance. Second, choosing a head-on collision allowed for a greater accumulated speed to be reached, resulting in greater kinetic force. By meeting the comet head-on, the relative velocity between the impactor and the comet was maximized. It wasn't just the speed of the impactor. It was the combined speed of the impactor rushing towards the comet and the comet rushing towards the impactor. This combined velocity meant a higher kinetic energy upon impact, and thus a larger, more scientifically revealing crater. It was about delivering the most powerful, yet precisely controlled scientific punch possible, ensuring that enough material would be excavated to expose the ancient interior. This strategic choice was a testament to the mission's meticulous planning, turning a seemingly simple collision into a highly optimized scientific experiment. The final hours must have been excruciating for the team back on Earth. The impactor targeting sensor was relentlessly beaming back images, each one a progressively closer view of Tempel 1, revealing more and more of its pockmarked ancient surface. These images captured moments before oblivion were themselves invaluable, offering insights into the comet's small-scale features that no previous mission could match. The tension in the control room would have been thick, a silent prayer whispered with every incoming data packet. And then it happened. On July 4th, 2005, just 1 second out from the anticipated arrival time, the impactor met its destiny. It was an astonishing feat of precision. Imagine predicting the exact second of an event millions of miles away and being off by only a blink of an eye. The impactor hit Tempel 1, not with a gentle tap, but with a mighty unyielding force, a culmination of billions of years of cosmic history meeting a fleeting moment of human ingenuity. And what a magnificent spectacle it produced. From the flyby spacecraft's vantage point, and observed by countless telescopes back on Earth, there was a tremendous release of energy. The impact delivered 1.96 EX 10 TNT joules worth of energy, thanks to the impactor's incredible speed of approximately 37,000 kilometers per hour. To put that immense energy into a more relatable context, it was roughly equivalent to 5 tons of TNT exploding. It was not an explosion in the traditional sense driven by chemical reactions, but rather a purely kinetic event where the immense energy of motion was suddenly converted into heat light and the violent expulsion of material. It was a controlled cosmic firework designed not for destruction, but for unparalleled illumination. What's more, the impact created an immediate dramatic visual. Dust plumed into space in a massive burst, a glorious expanding cloud of primordial material erupting from the comet's hidden depths. This wasn't just a puff. It was a vast fan-shaped cloud, rapidly expanding outwards from the impact site, glowing intensely in the sunlight. These two factors, the immense energy release and the sudden massive burst of dust, combined to create a flash much brighter than scientists were expecting. This unexpected brilliance was a testament to the sheer energy of the impact, and perhaps a hint at the properties of the material that had just been excavated. Scientists watching from Earth and through the eyes of the flyby spacecraft were absolutely thrilled that they had struck so accurately. The precision was astounding, a testament to the years of work, the meticulous calculations, and the flawless execution of the spacecraft's autonomous systems. The direct hit was confirmation that the most challenging part of the mission, the controlled collision, had been a resounding success. This was the moment of truth, the culmination of a decade of dreams and dedicated effort, proving that humanity could indeed reach out and touch an ancient cosmic wanderer, forcing it to momentarily reveal its innermost secrets. The light of that impact, brief yet profound, illuminated not just the comet, but the remarkable capabilities of human curiosity and ingenuity. The flash of light from the impact, so much brighter than anticipated, was a testament to the colossal energy unleashed. It was a fleeting cosmic beacon, signaling the success of the most audacious part of the Deep Impact mission. Scientists glued to their monitors felt a profound thrill. They had struck so accurately a bullseye across millions of miles of empty space. This precision was exhilarating, a culmination of years of meticulous planning and flawless execution. The initial reports were triumphant, a perfect hit, a monumental release of energy, and a spectacular plume of dust. However, in a peculiar twist of cosmic irony, the very success of the first part of the mission led to an unexpected negative side effect. The tremendous energy released by the impact had indeed excavated a significant amount of material, just as hoped. But this dramatic expulsion of dust formed an incredibly large and dense dust cloud that lingered around the impact site. Imagine trying to take a picture of a precise spot on a dusty road after a sudden powerful gust of wind has kicked up a massive cloud of dirt. That's essentially what happened. This colossal dust cloud, a direct result of the kinetic power of the impact, obscured the flyby's view of the impact crater. The very event designed to reveal the crater had momentarily hidden it from its primary observer. This was a moment of bittersweet realization for the scientists. The impact itself was magnificent, a testament to their engineering prowess. But now the primary scientific goal, precisely measuring and characterizing the crater, was suddenly shrouded in uncertainty. The dust wasn't just a brief puff. It outgassed from the comet for the next 13 days, a continuous stream of material boiling off the newly exposed volatile interior. This outgassing peaked 5 days in becoming most intense and creating the densest veil during that period. This persistent shroud made it incredibly hard to see the results of this interstellar bullseye, frustrating the immediate gratification of direct observation. It was like trying to observe a delicate surgical procedure through a continuously swirling mist, making the details elusive and the immediate assessment challenging. Yet even this unexpected dust cloud, which initially seemed to be a hindrance, offered some interesting insights into the internal pressures going on inside the comet. The sheer volume and duration of the outgassing suggested that the impact had exposed a highly volatile region. Perhaps pockets of ice that were previously insulated now suddenly exposed to the sun's warmth. The sustained release of material indicated a dynamic internal environment where pressures and volatile compounds were actively interacting within the comet's porous structure. It was a live demonstration of the comet's icy heart awakening under a sudden forceful stimulus. This unintended consequence became a scientific clue in itself, offering a glimpse into the comet's respiration after its deep cosmic wound. The sheer scale of the material expelled was staggering. Around 5 million kilograms of water and between 10 and 25 million kilograms of dust were ejected from Tempel 1 in that time. To put that into perspective, 5 million kilograms of water is enough to fill 2 Olympic-sized swimming pools, and 10 to 25 million kilograms of dust is equivalent to the weight of many thousands of cars. This enormous expulsion of material, a mix of ancient ice and primordial dust, was a powerful confirmation that the impactor had indeed penetrated deep into the comet's interior, exposing significant quantities of previously undisturbed material. It was a truly massive cosmic eruption, painting a temporary new glowing portrait of Tempel 1. While the immediate direct view from the flyby was hampered, scientists are nothing if not resourceful. Fortunately, they were able to rely on other eyes to finish up Deep Impact's mission. The beauty of modern astronomy lies in its interconnectedness, a global network of silent watchers. The collision had been observed through numerous other telescopes on or around Earth. This included some of the most powerful instruments of our time, like the Hubble Space Telescope, positioned in Earth orbit, free from the blurring effects of our atmosphere, capable of observing with unparalleled clarity. The Swift satellite, primarily an X-ray and gamma-ray telescope, also turned its gaze, offering a different spectral view of the impact's energetic aftermath. These powerful professional observatories provided crucial data capturing the event from various angles and across different wavelengths of light, helping to piece together the full picture of the impact. But the reach extended even further to the passionate network of amateur astronomers. Many amateur astronomer telescopes around the world, equipped with surprisingly sophisticated digital cameras, also turned their lenses towards Tempel 1, eager to witness this unprecedented event. This widespread observation network, from the giants of professional astronomy to the dedicated enthusiasts in their backyards, created a truly global spectacle and a rich, diverse data set. Each observation point, however small or large, contributed a unique perspective to the cosmic tapestry being woven by the impact. This collaborative spirit, where professional and amateur efforts converged, underscored the universal fascination with the mission and its profound implications. While these multispectral observations provided a wealth of information about the composition and dynamics of the ejected plume, they still couldn't offer a precise, high-resolution image of the actual crater. The dust cloud, even from distant perspectives, still limited the clarity needed for detailed morphological analysis. The scientific hunger for a clear view of the impact site persisted a quiet yearning for the definitive visual proof of their groundbreaking experiment. And so years later, the universe provided an unexpected answer from an old friend. Another spacecraft called Stardust entered the scene. Stardust had already completed its primary mission of collecting dust samples from Comet Wild 2 and returning them to Earth in 2006. Its original mission was over, but it still had fuel and functional instruments. In a testament to human ingenuity and the flexible nature of space missions, Stardust was repurposed and redirected for an extended mission. Its new objective to fly past Tempel 1 and to take photos of the impact crater created by Deep Impact years earlier. This repurposing was like sending a veteran explorer back to a famous historical site to finally inspect a detail that was missed on the initial hurried visit. Stardust successfully carried out this extended mission a few years later, in 2011. Imagine the quiet excitement as Stardust, gracefully maneuvering through space, finally approached Tempel 1 years after the dramatic collision. Its cameras, designed for close-up imaging, began to snap pictures of the comet's surface. And there it was, a clear, unmistakable scar on the ancient face of Tempel 1, the impact crater. From the images it took, scientists were finally able to spot the crater, a tangible testament to Deep Impact's success. The Stardust images were not just visually striking. They provided crucial quantitative data. Scientists were able to calculate that the crater was approximately 150 meters across, a significantly larger feature than initially predicted from the immediate impact flash. This meant it was 50% larger than they were predicting, a substantial difference that held profound implications for understanding the comet's interior. This larger-than-expected size was the first concrete clue to the comet's surprising properties. It was a direct, undeniable piece of evidence unveiled by the patient, persistent efforts of multiple spacecraft and years of dedicated observation. The wait was long, but the reward was immense, providing the clearest picture yet of the result of humanity's gentle but firm cosmic punch. And from this definitive measurement of the crater's size, combined with the earlier observations of the dust plume, scientists learned something truly profound about Tempel 1. Its surface was a very fluffy material. It was not a hard, dense block of ice. Instead, it was found to be made from more dust than was expected, and its substance was much finer and less compacted than even a powdered snowbank. Imagine trying to push your hand into a freshly fallen, very light snowdrift. That's the kind of soft, yielding material Deep Impact had encountered. This realization shattered some long-held assumptions about cometary nuclei. It suggested that Tempel 1 was far less consolidated, far more delicate than many had previously theorized. The implications of this fluffiness were staggering. The surface was incredibly porous. In fact, through meticulous analysis of the impact dynamics and the crater's characteristics, scientists were able to estimate that an astonishing 75% of the comet was actually empty space. Think about that for a moment. 3/4 of Tempel 1 was literally void, a cosmic sponge of ice and dust with vast interconnected pockets of emptiness within its structure. This made it far less dense than a typical rock or even a solid block of ice. The entire thing, this colossal ancient wanderer, was held loosely together by gravitational forces, a fragile celestial aggregate of primordial material. It was more like a loosely packed cosmic sandcastle or a giant ethereal dust bunny rather than a solid icy cannonball. This discovery fundamentally reshaped our understanding of how comets might have formed and how they have evolved over billions of years, suggesting a gentler, more gradual accumulation of material in the cold, distant regions of the early solar system. This extreme porosity was a revelation. It indicated that comets might be far more fragile and less coherent than previously imagined, essentially giant piles of loosely aggregated material. This has implications for how comets might survive their journeys through the solar system and how they might fragment or break apart over time. It also offers clues about the conditions in the early solar system where they formed. Such a fluffy structure suggests very low velocity collisions during their formation, where particles gently stuck together without much compaction. It paints a picture of a calm, almost serene process of accretion in the deep freeze of the solar system's outer reaches. The analysis didn't stop at the physical structure. From a meticulous analysis of the plume that had been ejected from Tempel 1, after the impact, scientists were able to identify several interesting material components. The light from the plume, fractured by spectrographs, revealed the distinct fingerprints of various elements and molecules. These included clays, suggesting the presence of water in liquid form at some point in the comet's history, or the early solar nebula before the comet formed. They found silicates, the basic building blocks of rock, much like the minerals found in sand and glass on Earth. The presence of sodium was also detected, adding to the rich cocktail of primordial ingredients. But perhaps the most tantalizing discovery was the presence of organic material. These weren't signs of life itself, no tiny cosmic microbes, but rather complex carbon-rich materials, the very foundational chemistry from which life can emerge. These molecules are the building blocks of life as we know it, containing carbon, hydrogen, oxygen, and nitrogen, arranged in complex ways. Finding them deep within a pristine comet, untouched by the sun's harsh radiation for billions of years, was a profound moment. It suggested that these vital ingredients, the raw chemical precursors to life, were present in the early solar system from its very beginning, incorporated into these icy wanderers. The implications of finding such organic material are immense and deeply philosophical. While not life itself, these heavily rich carbon materials may have been carried to Earth by comets in the past. Imagine our early Earth, a young volatile planet, still cooling from its fiery birth. Could it be that billions of years ago, as comets like Tempel 1 periodically swung through the inner solar system, some of them delivered these precious organic payloads to our planet's surface? These cosmic deliveries could have provided the vital materials that make up life here, effectively seeding our world with the necessary chemical ingredients for evolution to begin. It's a breathtaking thought that we as living beings might owe a part of our very existence to these ancient icy wanderers, these quiet cosmic messengers carrying the seeds of creation across the vast, dark expanse of space. So there we have it, a recap of the Deep Impact mission to Tempel 1, a journey that began with ancient superstitions and culminated in a profound scientific revelation. All in all, the mission was a big success. It didn't just confirm theories, it surprised us, revealing a comet far fluffier and more porous than many had imagined, and hinting at a primordial composition rich in the building blocks of life. It was a triumph of scientific ingenuity, patience, and a willingness to embrace the unexpected. But the story of Deep Impact wasn't quite finished there. Its quiet journey had another chapter waiting to unfold, a further exploration into the boundless wonders of our solar system. The successful impact on Tempel 1 and the remarkable insights gleaned from the colossal dust plume marked a triumph. Yet the story of discovery was far from over. While the initial view of the crater from the Deep Impact flyby was indeed obscured by the very success of the collision, the scientific quest for a clear image of that precious scar, that window into the comet's ancient heart, persisted. It was a testament to the patient, collaborative spirit of scientific exploration, a quiet determination to unearth every possible truth. Imagine for a moment the frustration of a painter who has just applied the perfect vibrant stroke to their canvas, only for a sudden gust of wind to kick up a cloud of dust, momentarily obscuring their masterpiece. That's what the Deep Impact team faced. The large dust cloud kicked up by the impact lingered, a swirling, luminous veil that stubbornly refused to dissipate quickly. This was the ironic consequence of such a powerful kinetic event. The very action designed to reveal a fresh surface instead shrouded it in mystery. The dust outgassed from the comet for a full 13 days, peaking 5 days in creating a persistent, dense fog that made it hard to see the results of this interstellar bullseye from the primary observation spacecraft. It was like trying to peer through a thick cosmic fog, where the precise details of the newly formed crater remained tantalizingly out of reach. Yet even in this unexpected challenge, there was a quiet triumph. The prolonged outgassing, the sheer volume of dust and ice persistently erupting from the comet offered a unique and valuable insight. It wasn't just a nuisance, it was a live demonstration of the comet's volatile nature, hinting at the internal pressures and the deep reservoirs of frozen gases and dust within. The continuous expulsion suggested that the impact had indeed tapped into a significant active region of the comet's interior, a place where primordial ice was still readily sublimating under the brief influence of the sun's warmth, even from afar. This sustained activity was a scientific clue in itself, offering a glimpse into the dynamic hidden life of a cometary nucleus. It was a subtle whisper from the comet's heart, even if its face remained momentarily hidden. The sheer scale of the ejected material was truly breathtaking, around 5 million kilograms of water, and between 10 and 25 million kilograms of dust were flung from Tempel 1. To visualize this, consider that 5 million kilograms of water is roughly the weight of 2,500 standard cars, or enough to fill 2 Olympic-sized swimming pools. The dust up to 25 million kilograms is equivalent to the weight of over 5,000 African elephants. This wasn't a small puff. It was a cosmic eruption, a massive volume of ancient primordial material expelled into space, glowing faintly in the distant sunlight. It confirmed that deep impact had truly made a deep penetration reaching far beyond the weathered surface into the comet's fresh, untouched interior. This colossal expulsion of material, a mix of ancient ice and primordial dust, transformed Tempel 1 into a temporary, magnificent cosmic geyser, a unique spectacle witnessed across the solar system. While the deep impact flyby's view was temporarily hampered, the beauty of modern astronomical research lies in its interconnectedness and global collaboration. Fortunately, scientists were able to rely on other eyes to fill in the missing pieces and complete the observational puzzle of Deep Impact's mission. Imagine a vast, silent network of cosmic watchers, all turning their gaze towards a single dramatic event. The collision had been observed not just by the Deep Impact spacecraft, but through numerous other telescopes on or around Earth. These included some of the most powerful and sophisticated instruments in our astronomical arsenal. The Hubble Space Telescope, positioned above Earth's atmosphere, offered an unparalleled clarity of view, free from the blurring effects that plague ground-based observatories. Its keen eye was turned towards Tempel 1, diligently recording the event. The Swift satellite, primarily designed to detect gamma-ray bursts, also reoriented itself to observe the comet, providing unique data in X-ray wavelengths, which could reveal different energetic processes occurring during and after the impact. These professional observatories, each with its unique capabilities, provided crucial complementary data, capturing the event from various angles and across different wavelengths of light. They were like different instruments in a cosmic orchestra, each playing its part to create a fuller, richer understanding of the impact's symphony. But the reach of observation extended even further to the passionate and dedicated community of amateur astronomers. Many enthusiasts around the world, armed with their own telescopes and surprisingly sophisticated digital cameras, also turned their lenses towards Tempel 1. Their contributions, often overlooked but invaluable, added to the collective data, sometimes providing continuous coverage from different longitudes as Earth rotated. This widespread observation network, from the giants of professional astronomy to the diligent enthusiasts in their backyards, created a truly global spectacle and a rich, diverse data set. This collaborative spirit, where professional rigor met amateur passion, underscored the universal fascination with the Deep Impact mission and its profound implications, making it a truly shared human endeavor. While these multispectral observations provided a wealth of information about the composition and dynamics of the ejected plume, telling us what was thrown out, they still struggled to provide a precise, high-resolution image of the actual crater itself. The sheer volume and persistence of the dust cloud, even from distant perspectives, still limited the clarity needed for a detailed morphological analysis of the impact site. The scientific hunger for a clear, crisp view of the impact scar persisted, a quiet yearning for the definitive visual proof of their groundbreaking experiment. It was a missing piece, a tantalizing blank spot in the otherwise vibrant tapestry of observations. And so years later, the universe provided an unexpected answer, not from a new mission, but from an old friend. Another spacecraft called Stardust entered the scene unexpectedly, extending its remarkable journey. Stardust had already made history with its primary mission. It had successfully collected dust samples directly from Comet Wild 2's coma, and even more remarkably, returned them safely to Earth in 2006. Its original mission was considered complete, a resounding success in its own right. But as fate would have it, Stardust still had fuel on board, and its instruments were largely functional. In a testament to human ingenuity, flexibility, and the long-term vision of space agencies, Stardust was repurposed and redirected for an extended mission, a second act in its cosmic ballet. Its new audacious objective to fly past Tempel 1, the very comet deep impact had struck, and to finally take those elusive close-up photos of the impact crater created years earlier. This repurposing was like sending a veteran explorer who had already brought back tales from one distant land on a new crucial expedition to verify a key detail missed on a previous hurried visit to another. It was a brilliant, cost-effective way to maximize scientific return from an already accomplished spacecraft. Stardust successfully carried out this extended mission a few years later in 2011 on its aptly named Epoxy mission, part of which was a continuation of Deep Impact's observations known as Deep Impact Extended Investigation. Imagine the quiet excitement as Stardust, gracefully maneuvering through space, finally approached Tempel 1 years after the dramatic collision. Its navigation systems, honed by its previous cometary encounter, guided it with precision. Its cameras, designed for close-up imaging of cometary nuclei, began to snap pictures of Tempel 1's surface as it sped past. And there it was, after years of waiting, a clear, unmistakable scar on the ancient face of Tempel 1, the impact crater. From the images it took, scientists were finally able to spot the crater, a tangible visual testament to Deep Impact's success years in the making. The Stardust images were not just visually striking, a beautiful confirmation of the impact. They provided crucial quantitative data. Scientists meticulously analyzed the photographs, meticulously measuring the dimensions of the newly revealed cavity. They were able to calculate that the crater was approximately 150 meters across, a significantly larger feature than initially predicted from the immediate bright impact flash observed by the flyby. This meant it was 50% larger than they were predicting, a substantial difference that held profound implications for understanding the comet's interior. This larger-than-expected size was the first definitive concrete clue to the comet's surprising properties, a direct, undeniable piece of empirical evidence finally unveiled by the patient, persistent efforts of multiple spacecraft and years of dedicated observation. The wait was long, but the reward was immense, providing the clearest picture yet of the result of humanity's gentle but firm cosmic punch. And from this definitive measurement of the crater's size, combined with the earlier observations of the dust plume and the dynamics of the impact, scientists learned something truly profound about Tempel 1. Its surface was a very fluffy material. It was not a hard, dense block of ice, as some theories had posited. Instead, it was found to be made from more dust than was expected, and its substance was much finer and less compacted than even a powdered snowbank. Imagine trying to push your hand into a freshly fallen, very light snowdrift. That's the kind of soft-yielding, highly porous material Deep Impact had encountered. This realization shattered some long-held assumptions about cometary nuclei, suggesting that Tempel 1 was far less consolidated, far more delicate than many had previously theorized. It was a cosmic surprise, forcing a re-evaluation of our models of cometary structure. The implications of this fluffiness were staggering. The surface was incredibly porous, almost like a sponge. In fact, through meticulous analysis of the impact dynamics and the crater's characteristics, scientists were able to estimate that an astonishing 75% of the comet was actually empty space. Think about that for a moment. 3/4 of Tempel 1, a body kilometers across, was literally void, a cosmic sponge of ice and dust with vast interconnected pockets of emptiness within its structure. This made it far less dense than a typical rock or even a solid block of ice. The entire thing, this colossal ancient wanderer, was held loosely together by gravitational forces, a fragile celestial aggregate of primordial material, like a loosely packed cosmic sandcastle, or a giant ethereal dust bunny, rather than a solid icy cannonball. This discovery fundamentally reshaped our understanding of how comets might have formed and how they have evolved over billions of years, suggesting a gentler, more gradual accumulation of material in the cold, distant regions of the early solar system, where particles drifted together almost imperceptibly. This extreme porosity was a revelation. It indicated that comets might be far more fragile and less coherent than previously imagined, essentially giant piles of loosely aggregated material. This has implications for how comets might survive their journeys through the solar system and how they might fragment or break apart over time, perhaps explaining some of the comet outbursts observed by telescopes. It also offers crucial clues about the conditions in the early solar system where they formed. Such a fluffy structure suggests very low-velocity collisions during their formation, where particles gently stuck together without much compaction. It paints a picture of a calm, almost serene process of accretion in the deep freeze of the solar system's outer reaches, a slow, quiet assembly of cosmic dust and ice. This was a direct physical insight into the very mechanics of planetesimal formation, offering a tangible link between a modern space mission and the deepest cosmic past. Beyond the physical revelations of Tempel 1's fluffy, porous interior, the Deep Impact mission offered an even more profound glimpse into the fundamental building blocks of our existence. From a meticulous analysis of the plume that had been ejected from Tempel 1, after the impact, scientists were able to unravel its chemical secrets. Imagine the ejected material as a vast ephemeral cloud of ancient cosmic ingredients, momentarily illuminated by the sun's distant glow. By carefully studying the light reflecting from and emitted by this plume, using advanced spectroscopic techniques, a bit like reading a cosmic barcode, scientists could identify the distinct fingerprints of various elements and molecules within. This chemical detective work revealed a fascinating array of components. They found clay's complex minerals that often form in the presence of liquid water. Their discovery within a comet, a body thought to be largely frozen, hints at intriguing possibilities. Perhaps these clays formed in the early solar nebula before being incorporated into the comet. Or perhaps they point to pockets of liquid water existing within comets at certain points in their history. Or even to hydrothermal activity in the comet's warmer interior during its formation. This presence of clays adds another layer of complexity to the comet's primordial story, suggesting processes that might have required conditions beyond simple deep freeze. They also identified silicates, the most common mineral group on Earth, forming the basic building blocks of rock, much like the sand on a beach or the quartz in a crystal. Finding these familiar terrestrial components within a comet reinforced the idea that comets are made from the same raw materials that eventually coalesced to form our rocky planets. It's a quiet reminder of the deep shared ancestry of all matter in our solar system, a cosmic family tree connecting the smallest grain of sand to the largest planet. The presence of sodium was another interesting detection, adding to the rich cocktail of primordial ingredients. Sodium is a relatively volatile element, meaning it vaporizes easily, and its detection further contributed to our understanding of the thermal history and evolutionary processes of comets. Each detected element, each molecule identified, was like a tiny puzzle piece, slowly fitting together to reveal a clearer picture of the environment in which Tempel 1, and indeed our entire solar system, first took shape. But perhaps the most tantalizing and philosophically resonant discovery was the unequivocal presence of organic material. Now it's crucial to understand what this means and what it doesn't. This wasn't a discovery of life itself, no tiny cosmic microbes or ancient alien spores. Instead, these were complex carbon-rich materials, intricate molecules containing carbon, hydrogen, oxygen, and nitrogen, arranged in ways that form the very foundational chemistry from which life on Earth can emerge. These are the building blocks of life as we know it, the intricate molecular Lego pieces from which proteins, DNA, and all the machinery of living cells are constructed. Finding such organic molecules deep within a pristine comet material that had been frozen and largely untouched by the sun's harsh radiation for billions of years was a profound moment for astrobiology and our understanding of life's cosmic origins. It suggested that these vital ingredients, these raw chemical precursors to life, were not unique to Earth. Instead, they were ubiquitous in the early solar system, present from its very beginning, incorporated into these icy wanderers, and likely abundant in the swirling cloud of gas and dust from which our sun and planets were born. It fundamentally shifts our perspective from a purely Earth-centric view of life's beginnings to one that is deeply interconnected with the cosmos. The implications of finding such organic material are immense and deeply philosophical, resonating with the grandest questions humanity has ever asked. While not life itself, these heavily rich carbon materials may have been carried to Earth by comets in the past. Imagine our early Earth, a young, tumultuous planet still cooling from its fiery birth, its oceans forming, its atmosphere stabilizing. It was a crucible, but perhaps it needed a cosmic kickstart. Could it be that billions of years ago, during a period known as the Late Heavy Bombardment, as comets and asteroids bombarded the inner solar system, some of them delivered these precious organic payloads to our planet's surface? These cosmic deliveries, falling through the early atmosphere like gentle life-giving rain, could have provided the vital materials that make up life here. They might have enriched the primordial oceans with the necessary chemical ingredients, the very soup from which evolution could begin its slow, miraculous dance. This concept paints a breathtaking picture that we as living beings might owe a part of our very existence, our very molecular makeup, to these ancient icy wanderers. Comets, once feared as harbingers of doom, are transformed into cosmic gardeners, silently tending to the seeds of life, delivering them across the vast, dark expanse of space to nascent planets. It suggests that life's origins might not be a purely terrestrial story, but a cosmic one, a grand narrative woven into the very fabric of the universe. It's a thought that humbles and elevates us simultaneously. We are not just children of the Earth, but perhaps in a very real sense, children of the comets as well, connected by ancient molecular threads to these distant, beautiful, icy relics. This discovery adds a crucial layer to the ongoing scientific debate about the origin of life. For a long time, one of the great mysteries has been how the complex organic molecules necessary for life, such as amino acids, the building blocks of proteins and nucleobases, the building blocks of DNA, first appeared on early Earth. Were they synthesized in situ, through lightning strikes and volcanic activity in Earth's early atmosphere, as in the famous Miller-Urey experiment? Or were they delivered from space? The deep impact findings strongly support the latter, the exogenesis hypothesis, suggesting that a significant portion of Earth's early organic inventory might have been supplied by comets and other extraterrestrial objects. Imagine the early Earth bombarded not just by destructive impacts, but by life-giving packages from the cold outer reaches of the solar system. Each comet strike, while potentially disruptive, could also have been a delivery service enriching the planet with the raw chemical ingredients needed for complexity to arise. It's a powerful, almost poetic idea that the very violence of cosmic collisions might also have been a catalyst for creation, delivering the sparks that ignited life. The comets, once seen as sterile cold bodies, are transformed into cosmic nurseries, harboring the dormant potential for life, waiting for the right conditions to awaken. The organic materials found in the Tempel 1 plume were complex, including hydrocarbons and nitriles, which are classes of molecules involved in forming amino acids and other biological compounds. While these are not themselves alive, their presence indicates that the necessary chemical precursors were available. It suggests a universal recipe for life where the fundamental ingredients are spread throughout the cosmos, waiting for the right planetary conditions to come together. This means that the processes that led to life on Earth might not be unique, but rather a common occurrence wherever suitable planets form and comets can deliver their valuable cargo. This revelation from Deep Impact pushes us to expand our understanding of the universe beyond the familiar. It nudges us towards the exciting possibility that life in its most fundamental chemical form might be seeded throughout the galaxy. If comets everywhere harbor these organic building blocks, then the potential for life to emerge on other planets or moons becomes even more compelling. It encourages us to look for signs of life, not just in the habitable zones around stars, but also in the icy depths of moons like Europa or Enceladus, where cometary material might have been preserved or even triggered early chemical reactions. The Deep Impact mission, by revealing the organic richness of a single comet, opened a profound window onto the potential for life elsewhere in the cosmos. So there we have it, a recap of the Deep Impact mission to Tempel 1, a journey that began with ancient superstitions and culminated in a profound scientific revelation. This mission didn't just confirm existing theories. It surprised us, revealing a comet far fluffier and more porous than many had imagined, and most crucially hinting at a primordial composition rich in the building blocks of life. It was a triumph of scientific ingenuity, patience, and a willingness to embrace the unexpected. The data it sent back, collected through a combination of initial observations and later serendipitous follow-ups, offered an unparalleled look into the ancient heart of a comet. It redefined our understanding of comets from mere dirty snowballs to complex porous structures that are vital repositories of early solar system material, including crucial organic molecules. The success of Deep Impact wasn't just in creating a crater. It was in the profound insights that crater and its ejecta provided, altering our cosmic perspective. It underscored the fact that sometimes, to understand the deepest truths, one must dare to make a deep impact, a deliberate transformative interaction with the very objects of our inquiry. The light of that impact, brief yet profound, illuminated not just the comet, but the remarkable capabilities of human curiosity and ingenuity, pushing us closer to answering one of humanity's oldest questions: where do we come from? But the story of Deep Impact wasn't quite finished there. Its quiet journey had another chapter waiting to unfold, a further exploration into the boundless wonders of our solar system, a legacy that extended far beyond its initial dramatic moment. The spacecraft, having delivered its powerful punch, still had a vital role to play, a new mission to embark upon, continuing its silent vigil across the vastness of space. Its work and its contributions to our understanding of the cosmos were far from over. The dramatic collision with Tempel 1 and the profound scientific insights it delivered marked a crowning achievement for the Deep Impact mission. It had successfully pierced the veil of a comet's interior, revealing secrets about its primordial structure and composition. But the story of the Deep Impact spacecraft itself did not end with that glorious cosmic fireworks display. Like a seasoned explorer who has completed one grand expedition only to embark on another, the flyby spacecraft, the mothership that had observed the impact, was later given a new mission. Its journey and its contributions to our understanding of the cosmos were far from over. This new mission was formally entitled EPOX-E, an acronym that elegantly summarized its twin objectives: extrasolar planet observation and Deep Impact extended investigation. This creative repurposing of an already successful spacecraft was a testament to the ingenuity of space engineers and scientists, a way to maximize the scientific return from an incredibly valuable asset already far out in space. EPOX-E was designed to leverage the flyby spacecraft's existing capabilities, particularly its powerful telescopes and cameras for entirely new and exciting frontiers of discovery. It was a second life for a robotic pioneer, a new chapter written not in an old book, but on the vast blank pages of the cosmos. In 2007, the flyby spacecraft, now operating under its new epoxy mandate, began to head off on this extended journey. Its primary focus shifted from directly studying one comet to two distinct, yet equally captivating areas of astronomical research. One part of epoxy, the extrasolar planet observation component, turned the spacecraft's high-resolution imager towards distant stars, searching for the faint, telltale dips in brightness that signal the passage of an exoplanet across its star's face. Imagine using a highly sensitive light meter to detect the tiny shadow of a moth passing in front of a distant streetlight. That's the delicate art of exoplanet transit detection. Deep Impact's telescope, originally designed for cometary detail, proved remarkably adept at this precise photometric work, contributing valuable data to the burgeoning field of exoplanetary science. It was a quiet, diligent hunt for other worlds, a search for echoes of our own planetary system across the vast gulfs of interstellar space. The other part of epoxy, the Deep Impact. Extended investigation continued the spacecraft's legacy of cometary exploration. While it wouldn't perform another impact, it would conduct hundreds of thousands of photos of other comets, observing them from various distances and angles as they journeyed through the solar system. This was a different kind of study, a long-term observational campaign allowing scientists to track changes in cometary activity, study the evolution of their comas and tails, and perhaps even glimpse new active comets entering the inner solar system for the first time. It was a patient, sustained vigil, adding richly to our catalog of cometary behaviors and characteristics, expanding the insights gained from the dramatic Tempel 1 impact. Each photograph, each data point, was a quiet whisper from a distant icy world, contributing to a broader understanding of these ancient wanderers. The epoxy mission continued its silent, diligent work for several more years, faithfully transmitting its invaluable data back to Earth. It executed flybys of other comets, notably Comet Hartley 2 in 2010, providing close-up images and data that further complemented the insights gained from Tempel 1. These additional encounters allowed scientists to compare and contrast different cometary nuclei, helping to build a more comprehensive picture of their diversity and shared characteristics. The spacecraft, a solitary sentinel, truly maximized its lifespan and capabilities, becoming a workhorse of discovery in the deep expanse of space. However, even the most resilient robotic explorers eventually succumb to the harsh realities of space. In 2013, after years of faithful service, the Deep Impact flyby spacecraft ultimately dropped out of contact. The exact reason for the loss of communication remains unknown, but it is believed that a software glitch or a degradation of its orientation system led to it losing track of Earth, preventing it from pointing its antennae correctly for communication, or possibly draining its batteries. It was not a sudden dramatic explosion, but a quiet, fading, a gentle cessation of its cosmic transmissions. Imagine a distant lighthouse, its beam slowly dimming until it can no longer be seen, having guided countless ships to safe harbors. Deep Impact 2 completed its long vigil, fading silently into the interstellar darkness, its final messages unheard. But by then, Deep Impact had already done significant amounts to advance our understanding of comets and our solar system. Its legacy was firmly cemented in the annals of space exploration. The mission was a resounding success, not just in its dramatic execution, but in the profound knowledge it unearthed. It demonstrated the feasibility and incredible value of active, rather than merely passive, exploration of celestial bodies. It proved that we could indeed reach out and interact with these ancient wanderers, forcing them to reveal their hidden truths. The knowledge gained from Deep Impact's primary mission revolutionized our understanding of cometary interiors. The discovery that Tempel 1 was far more porous and fluffy than expected fundamentally changed models of comet formation, suggesting a gentler accretion process in the early solar nebula. This insight into their physical structure provides critical clues about the conditions of the early solar system, a snapshot of its birth that was preserved in ice and dust. It's like finding a perfectly preserved fossil that forces paleontologists to rethink the evolutionary timeline. Even more profoundly, the detection of organic material, the complex carbon-rich molecules that are the building blocks of life within Tempel 1's pristine interior, ignited a new wave of excitement in the field of astrobiology. It provided compelling evidence for the exogenesis hypothesis, the idea that comets may have delivered vital prebiotic ingredients to early Earth, potentially kickstarting the emergence of life on our planet. This transforms comets from mere icy curiosities into cosmic couriers, vital agents in the story of life, forging an ancient, intimate connection between ourselves and these distant, beautiful celestial wanderers. It pushes us to consider life not as an isolated terrestrial phenomenon, but as a possibility woven into the very fabric of the cosmos. The Epoxy Extended Mission 2 left its own valuable legacy. Its exoplanet observations contributed to the growing catalog of known exoplanets, helping to refine techniques for detecting and characterizing worlds beyond our solar system. Its continued observations of other comets provided crucial comparative data, highlighting the diversity among these objects and further enriching our understanding of their dynamics and evolution. Deep Impact, in its two distinct phases, became a multifaceted tool for cosmic discovery, extending its reach far beyond its initial dramatic purpose. The entire journey of Deep Impact, from its daring concept to its quiet farewell, is a profound testament to humanity's insatiable curiosity. It is a story of our unwavering drive to explore, to question, and to understand the universe that cradles us. It reminds us that even in the vast, silent expanse of space, our quest for knowledge is a vibrant, persistent force. The universe remains full of mysteries, but missions like Deep Impact provide us with ever-clearer windows through which to peer, revealing more of its intricate beauty and astounding complexity. So as we bring our gentle journey to a close for today, I hope you've found a quiet sense of wonder in listening to this podcast on the Deep Impact mission. It is a story that reminds us of the power of a question, the beauty of scientific exploration, and the enduring connection between our tiny planet and the boundless cosmos. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics as we continue to gently explore the wonders that lie beyond our earthly home. For now, I'm Alex McCohen, and this has been Astrum. All the best, and see you next time under the vast and wondrous canopy of stars. As we close our eyes, perhaps we can imagine those ancient comets, those silent, icy travelers still drifting through the cosmic dark, carrying within them not just the dust of stars, but the very secrets of creation, waiting for curious minds to reach out and touch them once more. The universe continues its endless silent dance, and we, with our humble questions and our soaring dreams, continue to listen.